15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2.
1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
Hello once again. Thank you for joining us on the Space Nuts podcast, the unsalted variety. This is episode 152, and my name's Andrew Dunkley. With me, as always, is Professor Fred Watson from the Department of Industry, Innovation and Science. I always forget the science part. Hello, Fred.
Hi, Andrew. Two old salts together, eh?
Yes, indeed. Yes, indeed. We've got a lot to talk about today. Some of it's ground we've been over before, but we things keep happening, so we need to keep updating, and that is that new gravity waves have been detected by LIGO, but there's a big question mark over some of these because in one case they don't know where it came from, which is a bit of a weird one. We also hear from Scottish space pilot Dave Mackay. Do you say Mackay or Mackay?
He would be Dave Mackay.
Mackay. He's back down to Earth after his Virgin test flight, which we did cover a little while back. And he's gone. I think he went back to his hometown to sort of say hello. He's a bit of a local hero, and not surprisingly. We've also got a couple of questions. These date back a little while, but we're doing some catch-up. We've had a question from Terry about the fabric of space being more rigid than steel. He can't get his head around it. And entangled particles interacting with a black hole and the potential rise of dark matter. Jens from Sweden wants to investigate that theory, and we will do so, Jens. So thank you for your questions. But first, Fred, let's get into these new gravity waves that have been picked up. I think I read a description that suggests that they may be or maybe not what they think they are. It would be like trying to listen to someone whisper in a noisy cafe.
Yes, that's right. So, yeah, remember, I mean, that's a really good analog because the LIGO detectors, and there are two of them at opposite corners of mainland USA, they are designed to detect very, very small vibrations, effectively. And they're not vibrations of the ground or vibrations of the air, they're vibrations of space. But the interesting thing about it is that they are right in the audio frequency range. The vibrations that LIGO is sensitive to are audible, except, of course, they're at an intensity that is very, very much less than anything our ears could hear. But if you amplify the signal up, you turn the vibration of space into a signal which can be amplified in an audio amplifier, then you can actually hear them. And what you hear is a kind of a chirp noise as the frequency goes up. And then at the end of it, the gravitational disturbance stops because it's all about things, coming together, the ones that have been detected so far. So this whoop sound is very much what you get from LIGO. And LIGO has had an upgrade. Remember, it was back in 2015 when the first gravitational waves were detected, but it's been working since then. It's actually technically called advanced LIGO because the original LIGO just wasn't sensitive enough to detect gravitational waves, so they worked on it again. This is several years ago, and it now can do. And so very soon after it was turned on, I think at the beginning of April, after the upgrades, they got a great signal from basically a neutron star collision. So that's two neutron stars coming together. And unlike black holes merging, when neutron stars merge, you get an electromagnetic signal. And there was an epic case, actually it was last year, when I think it was 70 observatories throughout the world combined to detect this collision in gamma rays, X-rays, ultraviolet, visible, infrared and radio waves.
And dogs and cats living together, it was a mess.
Exactly, all of that. So that's basically it confirmed that gravitational waves do travel at the speed of light, because the first gamma ray signal was detected, I think it was 1.3 or 1.7 seconds after the gravitational burst, and that's the time delay you'd expect for two neutron stars coming together to turn into gamma rays. Sorry, I'm kind of a little bit garbled there, but that is what we found last year. Now, that sort of event has happened again. There's been another neutron star signal from LIGO. I am not sure about whether the electromagnetic follow-up was done on those observations as well, but no doubt we'll find out when there's a major press release somewhere down the track. But what I think has excited people, and it's a little bit intriguing, is that a day after that neutron star merger, LIGO it detected a signal that was much less secure, if I can put it that way. Its intensity was not as great. And this is what you were alluding to at the beginning, like trying to pick up a conversation in a crowded restaurant or coffee bar or whatever, somebody whispering. The speculation is that this, for the first time, would be a collision between a black hole and a neutron star. And in fact, not so much a collision as a black hole swallowing up a neutron star.
Sounds more likely.
Yeah, neutron stars tend to be much less massive than black holes at a distance of 1.2 billion light years. Now, that's getting near the limit of detectability with LIGO. I think you're talking about, 1 point something billion light years as being the limit. So this is very, very excited. And one of the members of the LIGO scientific collaboration is quoted, is exactly the quotation that you've mentioned. We're especially curious about the April 26th candidate. Unfortunately, the signal is rather weak. It's like listening to somebody whisper a word in a busy cafe. It can be difficult to make out the word, or even to be sure that the person whispered at all. He says it will take some time to reach a conclusion about this candidate. So what's really interesting is that, they've actually released this now, saying, we've got something interesting which we're working on, rather than holding it all in and building up to a big press release in a year's time or something like that. Not only that, but there's been another 3 black hole collisions detected by LIGO. So they're really firing on all cylinders here, and it's fantastic stuff. It's really opened up the this new era of gravitational wave astronomy. It's almost starting to become routine when we pick up colliding black holes, as they expected it to do. They expected one a week, and they've kind of had one a week pretty well since the new version opened up. So now, exciting.
These collisions cause a gravitational wave, and I imagine that as it moves through the fabric of space, it dissipates, and by the time it gets to us, it's just a ripple.
Yeah.
What would it be like at the point of impact? I mean, if you were there. What would that be like?
Uncomfortable, I think, is the word.
That's probably an understatement.
I mean, if you're, so you're standing near a black hole, and ignore the fact that the black hole's trying to shred you up already, and this gravitational wave goes past where space is expanding and contracting. Can you imagine what that would do to your digestion? It would be all a bit grim. In fact, it might, it might not be that dramatic. I've never looked at the issues of what happens if you stand next to a collision emitting gravitational waves. I mean, all the other stuff would fry you anyway, probably. But I think the distances that we're detecting these things are quite near enough. Thank you. It's all very good. Yeah.
Now, you said that these things make a sound that we can't hear. We have to use electronics to be able to pick up the noise. Could a dog hear it?
No, it's far, well, yes, they could once it's amplified into an audio signal. It's really interesting. The high frequency cutoff is not in that ultrasound range that you expect animals to be able to pick up. It's basically middle A or something like that. It's a fairly moderate note. It's certainly not in the ultrasound range. So a dog could pick it up because they've got the same audio frequency range as we have, but plus that ultrasound level at the top of the frequency regime. Okay. So the answer is yes, but they'd still need all the signal to go through all the electronics.
They would need to process it through doggytronics to be able to hear it. So okay, I understand. All right.
Yes, of course. Doggytronics, yeah.
As always, we knew we'd be talking about this again because it's such a new and exciting discovery, and here we are. And I imagine there'll be more to come on gravity waves. You're listening to Space Nuts. Andrew Dunkley here with Fred Watson.
0G, and I feel fine.
Space Nuts.
2, 1, release.
Fire.
It's an incredible experience. I can tell that from just flying it as well. But on the last flight, having had someone in the cabin to unstrap, float around, move to the various windows, see what it's like in the vehicle as it's rotating, maneuvering in space. We're very excited about the results of that flight.
Welcome to Space Scotland.
Yes, there he is. He is a space pilot. He's from Scotland. His name is Dave Mackay, and that was him talking about his test flight in the Virgin Galactic craft, which looks like it's doing some amazing things, as is Dave. Fred?
Indeed, yeah.
Oh, and I must say that audio courtesy of the BBC, so we thank them for that because they do some good stuff in their science department at the BBC.
Indeed, they do. Absolutely, as does Dave in his cockpit on Spaceplane 2, the Virgin Galactic craft that he flew. Actually, it's called Unity, I think, if I remember rightly. So we talked about this flight, and you put your foot in your mouth when you described a person of the wrong gender being beside them, which was very entertaining, I have to say. But Dave, of course, the pilot, and the first time a Scotsman has gone into what I think in the military is called the limit of space. It's 50 miles, which is something rather more than it's 80 kilometers. They reached 90 kilometers in that flight, which is almost the Kármán limit. The Kármán limit is 100 kilometers, and that's where it's actually where the air is so thin that nothing you would do with fins would actually make any difference. That's what defines it, basically, the limit of space. So Dave Mackay from a tiny little town in Scotland called Helmsdale. It's in the Highlands in western Scotland. And Dave has a very, it's slightly modified, but unmistakably a Highland accent there with these comments. Because I was educated in Scotland at the University of St Andrews and then again at Edinburgh, a lot of my fellow students came from the Highlands and Islands district of Western Scotland, and their accents are very different from lowland Scotland. And, Dave's got exactly that lovely lilt that a lot of my friends and colleagues had. So it was very nice to hear it. So what did he do? Well, he piloted the space plane up to that height of 90 kilometers, came back. They had a person on board to test out the passenger experience, which is what happened. But then he's recently been back to the little town where he grew up, and he's talked to all the kids in the local school, which must be completely mind-blowing for them.
Yes.
Absolutely inspiring. And the thing that delighted me is that when Dave made that flight, he took with him the book he had as a child that inspired him to think about space as a career. It's a Ladybird book called Exploring Space. Now, Ladybird books were just a little bit late for my childhood, but certainly my children's childhood. They played a very big role, and Ladybird books they occupied many shelves of our bookcase at home when my two daughters were growing up. So Dave studied aeronautical engineering in Glasgow. He is now their Virgin Galactic's chief pilot, and that step that they made in February is a really big step forward. What I just wanted to add as a bit of a postscript to this story, Andrew, is that, as you know, last week I was in Kuala Lumpur at a conference that had as its theme space medicine, and I was setting some of the physical background for that. But one of the people that I talked to a lot there was an astronaut, Michael Barrett, who has flown to the space station twice. He's done 2 missions with some very interesting people along with him. But what impressed me was the respect with which he spoke about Virgin Galactic and their endeavours to make space tourism as safe as aviation is. Very strongly supportive. He emphasised that Virgin Galactic works closely with NASA, and many of the procedures that they follow are very, very similar. So that should be reassuring to anybody who's thinking of outlaying a couple $100,000 on a Virgin Galactic trip. I have currently saved up $23.50 for mine. And I think you've got even less than that, haven't you?
I'm saving $1 a week towards it, Australian, so that will take me 400,000 weeks.
That's right. Don't hold your breath. But it's a good news story, and it's just delightful. You don't have to look far on the BBC to find the rest of that audio and pictures of Dave Mackay visiting his hometown.
Yes, wonderful. And they really, I know they're behind schedule. They really wanted to have space tourism up and running by now, but you can't. You can't shortcut safety, and Richard Branson, being the kind of bloke he is not going to muck around with this. He wants it to work. He wants it to be right.
Exactly.
So we'll watch with interest, and who knows what the next nationality in space will be, Fred.
Yep. That's right. We will
tips?
Wait to see.
Is anybody sort of thinking, well, we should send up a Kazakhstani? Oh, they've probably already been. I don't know.
They fly all the time. No, look, the first proper passenger will actually be Richard Branson himself, with, I think, his son, if I remember rightly. He's got the seat on the first commercial flight, so he will, represent quite a lot of the English-speaking world, I guess.
I imagine so, but that'd be a good endorsement because he's testing his own product. So
absolutely,
that's
right.
the way to sell it. Definitely.
Yeah.
All right. And well done to Dave Mackay. I can't wait to see where he goes to next. You're listening to Space Nuts here with Andrew Dunkley and, of course, Fred Watson.
Okay, we checked all 4 systems and keying with a go.
Space Nuts.
Now, before we get on to some questions, just a reminder that we are now on YouTube. I mean, we're not doing video, not yet. We might do that sometime down the track, although I think that's pretty scary for you. And but if you put Space Nuts Podcast in your YouTube search, you should be able to find all of our episodes on YouTube these days, if that's your preferred platform. Terrific. And there are 4 people, Fred, that we have to send out a big hello to because we have 4 patrons on our Patreon account. So these are people who have volunteered to basically, help fund our podcast, which is fantastic. So if you are someone who might be interested in doing that, we're not going to tell you to. We're just going to put it out there as a possibility. Patreon, patreon.com/space nuts is where you need to go. Patreon.com/space nuts. And there are different values. You can put in $1 and help me get on the Virgin Galactic plane, or whatever you like. Now, Fred, we've got some questions, and this first one comes from Terry Johnson. G'day, Terry. Hi, gents. Hang for the show each week and can't wait for each episode. That's lovely. Was listening to a past episode about gravitational waves, which we've already talked about in this episode, as it turns out. Professor Fred mentioned that space fabric was 1 billion times more rigid than steel. Please explain. Don't get that at all. Sorry. It's doing my head in. That's a good way of describing how confusing that sounds. So, I guess we need to explain this, Fred.
Well, it does everybody's head in, because...
everyone thinks of space as emptiness. And,
yes, that's right.
And you float around in it. So how can it be more rigid than steel by 1 billion times?
Yeah, so maybe, and I should just add perhaps to your intro that it's a couple of months since Terry sent this question, so forgive us for taking so long to get to it, but it's a really interesting question. I think what you have to do is think about space as a kind of framework, and I don't know, the way I used to try and explain it to people was, can you think of those sort of climbing frames that you find in kids' parks where there's swings and and slides and all of that stuff? There's often climbing frames which are like sort of a cubic structure with basically just struts holding everything together, and that's kind of how I think of space.
Funnily enough, not how I think of it.
No, well, funnily enough, it's probably not how most people think of it. But I know, yes, I'm slightly different. But the point about space is it's not rigid like that. That it can bend. So if you imagine, that framework structure, and what makes it bend is mass. If you put a mass near there, then it's going to bulge slightly. And I can easily then imagine this climbing frame, with maybe a large child on it that's sort of bending slightly. And that's what space does. Even though we think of space as being nothing, it's not nothing. There is a kind of coordinate system framework in there, and it changes depending on the presence of matter. I think I probably said, not that it's a billion times more rigid than steel, but many billions of times more rigid than steel.
Wow.
Because I don't have the exact number to hand, but it is. And steel, we can imagine, because that's a lump of steel is easy to get your head around, and if you bang that, whilst it feels rigid, it feels like a solid thing. If you bang it with a hammer, it's going to ring, and that's telling you that there are vibrations going through it, which tells you that it has a level of flexibility. It's very rigid, is steel, but space is even more rigid, many billions of times more rigid. And if you bang space, which you can do with the odd black hole collision and things of that sort, then you will set it ringing. And that's more or less what happens with these gravitational waves. And just picking up a point, I'm coming from pedant's corner here, Andrew. They're not gravity waves, they're gravitational waves. Gravity waves are things that happen in clouds. They're caused by atmospheric turbulence. Just in case somebody phones in and says, you guys don't know what you're talking about because you're talking about gravity.
Oh, that happens all the time. I'm the one that has to go through these emails. I insulate you, Fred. I'm the one that cops it. No, seriously, we don't get much like that. But we get questions, or we get queries, or we get observations. Sometimes great photos. We got a whole batch of great photos from pilots' cockpits the other day, which
that's right. We did
amazing.
Noctilucent clouds.
Yeah, noctilucent clouds and storm clouds and all sorts of stuff. It was fantastic. We love that. But it seems that whenever we talk about something, it does prompt people to wonder about what else there is to know about that thing. And like when we started, we never envisaged doing a question and answer session, but it does seem to work, and it gives us an opportunity to talk about things that people want us to talk about,
exactly.
And opens up all those doors. So terrific. So Terry, thank you for your question. Hopefully that monkey bar theory. I called them monkey bars as a kid.
Yeah, that's right. That's the name I was looking for.
Monkey bar theory. There you go. So that if you've got a really big fat kid that you put on a monkey bar. That's a demonstration of the fabric of space and how strong it is.
There's nothing wrong with fat kids, Andrew.
No, of course not. Of course not. I was just being. Well, I wasn't. I was being awful. I was horrible. Let's move on. Now, this next question comes from Jens in Sweden. He says, so I've been thinking, if one or two entangled particles goes to a place without time, like a black hole, could this give rise to what we call dark matter? Is there some research on this? Woo, that's a tough one.
It's a really good one. So let me just read the important bit out. If one of two entangled particles goes to a place without time, like a black hole, so that in itself is really the answer to the question because entanglement suggests. So let's just backtrack to explain.
He's going to tell you it can't happen, Jens. That's what he's going to say.
It cannot happen. No, I'm not going to say that at all. So entanglement is when you've got two quantum particles, which usually means things that are very small. And let's think of photons of light, for example, particles of light. Two of them that maybe were emitted by the same laser. And the state of being in entanglement means that they behave like a single quantum particle. And you can actually separate them physically, and yet they maintain this entanglement. They maintain this behavior like a single particle. But if you look at one or prod it or something, have a look at it, then it will become disentangled and the other one will be instantly as well, no matter how far apart they are. So entanglement seems to defy the laws of physics in that you can do something to one particle and the other one will respond, even though they might be, a solar system apart. They will respond simultaneously.
I can't. That's doing my head in.
Yeah, it does mine in as well, and it does most people who study quantum physics in. So what it means is that entanglement, some quantum physicists believe that entanglement is revealing to us that there is another layer of reality beneath what we understand as space and time. There is a layer of reality that is independent of space and time. And that kind of fits in with relativity as well. Relativity and quantum theory seem to sit on top of this, whatever basis it is, that says there's no space and time. And entanglement is one of the reasons why people believe that. So you're already if you're an entangled particle, you are already in a regime where time does not operate in the same way that it does in the normal world. So that is, you don't really need to be inside a black hole for that to happen. Okay, could that give rise to what we call dark matter? I doubt it. I think this is probably much more in the realms of the physics of the universe rather than the physics of what is in the universe, which is what dark matter is. We know dark matter is some kind of subatomic particle, so it exists within a framework of space and time, although we haven't found it yet. And I think what we're talking about here, the entanglement, is at a layer below that. Now, it is possible that some phenomenon to do with whatever this spaceless, timeless regime is might reveal itself as looking like dark matter. But I wouldn't be surprised if people are actually working on this, because this is very much the kind of thinking that the subatomic particle physicists, particularly the ones who are looking at this theory called supersymmetry being hidden particles, massive hidden particles, and they're hidden by perhaps being in different dimensions, perhaps being independent of time and space. We don't know. But so the question that Jens asks is there some research on this? I bet you anything there is. I'm not aware of it and I'm not across it, but it might be interesting to have a look and find out. It's the kind of thing that you could Google or whatever other favorite search engine you use. Look up timeless, spaceless physics and see where it takes you.
Yeah, you never know. They might even answer your question better than
they
we
might.
can.
It's
But
better than I've done.
going back to the entangled particles, so you say if you prod one and it untangles, the other one squillions of billions of miles away will untangle as well. So it would be fair to say that if one of those entangled particles got sucked into a black hole, the other one would be released from the entanglement.
Yes, I think that's true. Yeah, because yes. And the reason is that no, you're quite right. So when I said prodding, what I should have said in physics terms is it interacted with its surroundings, because that's what seems to preserve the quantum state, this peculiar state where things can be right way up and upside down simultaneously, or where they can be in two places at the same time. That's called quantum superposition, and it only seems to exist if you isolate a particle from its surroundings, which is very difficult to do, but it can be done in a physics lab. So if you throw one of the entangled particles into a black hole, it will definitely interact with its surroundings, which means that the other one will become disentangled.
Wow. Okay. I actually figured something out.
You did?
Incredible.
You're a genius, Dunkley. That's why I talk to you.
I doubt that very much. Oh, dear. Jens, thank you for the question. We appreciate it. And hopefully you got some insight into your theory. But it opens up all sorts of possibilities when you're starting to talk about space-time, fabric of. I mean, there might be particles that are part of the fabric of space and time, and they are together and separate all at the same time across the entire universe. I mean,
it's kind of like
if we could figure that out, we could probably travel vast distances without even blinking.
I think we're entangled by space nuts.
Yes.
Which is definitely dimensionless physics, I think.
Anyway, I got a feeling that more questions will be prompted by that
Maybe
discussion.
That's what
Anyway, thank you for sending in the questions. We're trying to get through the back haul of them, starting at the bottom of the list. So if you sent one in recently, we'll get to that in 2021. Thank you, Fred, as always. Great fun.
Yeah, good to talk to you, Andrew. Take care, and we'll speak again next week.
We will indeed. Professor Fred Watson, astronomer, and from me, Andrew Dunkley, thank you as always. Lovely to be able to put this together for you, and thanks for all the wonderful emails and messages that you send us. Keep them coming, and we'll catch you next time on Space Nuts.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Subscribe to the full podcast on iTunes and Stitcher or your favourite podcast distributor. This has been another quality podcast production from Bytes.com.